We are going to talk about solutions. So first, a couple things about solutions. Some terms you might need to know to keep track of. Solution is just a homogeneous mixture of solvent and solute. They can be solids, liquids, or gases. We oftentimes think that solutions are only liquids, but a solution can be any sort of solid, liquid, or gas as long as it's a homogeneous mixture of solvent and solute. Some refreshing stuff from maybe from 6th grade science. You might have learned this stuff. Solute is what is being dissolved. It's usually present in the lesser amount. Solute is the substance being dissolved. So if you had, in this case, it looks like we have salt inside of water. The solute here would be the salt because it's what's going to be split apart and dissolved over time. The solvent is what is doing the dissolving. So in this case, the water would be the solvent. So the solvent is breaking apart the solute and dissolving it. And there are different types of solutions. There's gas in gas, so like air. There's a combination of all these different types of gases to make up the air that we breathe in our atmosphere. There can be a gas in a liquid solution. So like soda pop, we have CO2, that's the carbonation, that's what makes your pop be really bubbly when you open the bottle. And sometimes if you shake it and it'll pop up the top and explode everywhere, kind of. So that would be an example of a gas in a liquid. What happens is they force that CO2 into the water, and then when you open it, you let the CO2 be released from the water. Liquid in liquid is the most common type. Gasoline, there's a bunch of other types of things, liquid in liquid solutions. Solid in liquid, that would be like seawater or salt water. Any salts inside, so they're solid, and then you drop them in the water and they dissolve into the water. Gas in a solid, an example would be like hydrogen in the platinum or palladium. Hydrogen is gas. It can be forced into those solids there to form a solution. We have liquid in solid, dental amalgams. They put mercury in silver. If you remember, mercury is one of our 2 elements on the periodic table that is a liquid at room temperature. It's the only metal that's a liquid at room temperature. And then we have solid in solid. So if you remember making our gold pennies, we made that brass alloy with copper and zinc. We were mixing those 2 metals together. We were forming a solution between those. If you solder anything with tin and lead, that's also making a solution with 2 solids. So there's a couple different intermolecular forces that affect solubility. Sometimes the stronger the intermolecular attractions between the solute and the solvent. So remember, the solute is what is being dissolved. The solvent is doing the dissolving. The more they're attracted to each other, the more likely you're going to get that solute to dissolve completely. So examples, we have cyclohexane. It only has dispersion forces, so it's not water soluble. So you can't really get it to dissolve into water because it doesn't have very strong forces at all. Glucose, on the other hand, has hydrogen bonding, so it has super strong attraction for water, so it's very soluble in water. Miscible versus immiscible, like dissolves like. So like oil and water do not mix. If you've ever had oil pans after changing the oil in your car and then there's gotten water in it or rainwater in it, you can see them separate. If you ever are a baker and you've mixed vegetable oil in with your other liquids, you notice that they don't mix. Oil does not mix in very well. That's because oil is nonpolar and water is polar. And if they are not the same polarity, like one polar and one nonpolar, or either both polar or both nonpolar, they actually won't mix and won't dissolve into each other. So miscible is just when we say that they're soluble in one another, so they can mix. So polar liquids are soluble in other polar liquids, so you can mix water and alcohol because they're both polar, so they'll mix pretty well. But stuff like water and oil will not mix very well, or oil and alcohol does not mix. They stay separate. Other nonpolar liquids too, if they're both nonpolar, they can work together. So if you have acetone, that dissolves nail polish. And then immiscible is just the opposite of that. So they're not soluble in one another. So they cannot mix like oil and water. This is why, like when you have, since nail polish is nonpolar, that's why when you stick your nail polish into water or you're cleaning dishes and stuff like that, you notice that the nail polish doesn't come off every time you shower. But acetone is nonpolar, so acetone works to remove nail polish because it's the same, so it can dissolve and they can mix and form a solution. So it can mix, so it can remove that nail polish from your nails, but water will not. So there's an example of how this is applicable to like everyday life for us. So this is also important with solubility in vitamins. On the bottom left here, vitamin A is soluble in nonpolar compounds. This is because of its long hydrocarbon chain, and it only has one OH group at the very end of this hydrocarbon chain. chain, whereas vitamin C on the right here is soluble in water because it has 4 OH groups, which make for good hydrogen bonding sites. So those good hydrogen bonding sites, OH groups are great hydrogen bonding sites, so water is really going to want to bond to those spots, and it's going to dissolve that vitamin C. So here in this case we have water. Water is polar, so vitamin C must also be polar in this case. So vitamin C is water soluble. If you've heard of fat soluble and water soluble, your different vitamins. So vitamin A is soluble in nonpolar compounds. Your fat is nonpolar. So vitamin A would be a fat soluble compound because of that long hydrocarbon chain that makes it nonpolar. So this vitamin A would be fat soluble, vitamin C would be water soluble. So if you look at vitamin B6 on the left here and vitamin E on the right, see if you can guess which one would be fat soluble and which one would be water soluble based on what they look like. And yes, E would be the fat soluble one because it has that long chain again and still only one OH group on it. The other fat soluble vitamins are A, D, and K. It spells like ADEC to help you kind of remember what those are. If you've ever paid attention to your vitamins or heard about this, a lot of times wrestlers know really good what type of vitamins they should be taking based on if they're fat soluble or water soluble. So vitamin E is a fat soluble one because of that long hydrocarbon chain. B6 is water soluble, and water soluble is actually not stored in your liver or any other fatty tissues. It's just excreted by your kidneys. So your water soluble vitamins, whatever you have extra, you can't really overdose on water soluble ones because whatever you have extra in your body is just going to be excreted straight through you. Whereas your fat soluble vitamins, the extra will be stored in your liver and other fatty tissues. Technically you can overdose on these, but it most likely won't because it would take high concentrations, high amounts, so you don't really need to worry about it. But that's a lot of times people take water soluble, there's not really a dosage amount because it's just going to be excreted. It dissolves into the water and goes through your kidney, and your kidney excretes what it doesn't need. A couple things, this is also how soap works. So what soap does actually, soap or detergent can dissolve in water. So if you have like a bunch of grease on a surface, what happens is there's two sides to the soap or detergent structure. There's that long hydrocarbon tail, which remember those hydrocarbon chains are nonpolar. They also are hydrophobic. So hydrophobic means they are fearing water. So they will avoid being near the water side. So those nonpolar sides, those long little tail things off the end of the soap here, are going to go towards the grease because grease is also nonpolar, and water alone doesn't remove grease because water is polar and grease is nonpolar, so like does not dissolve like very well. So it's just like if you had oil, vegetable oil on your hands and you try to wash it off, you cannot get it off just with water. Usually you need to use some sort of soap. And it's because soap has two different sides, so it has that hydrocarbon chain, which is nonpolar, and it also has a short ionic head, which is polar and hydrophilic. And hydrophilic just means the opposite of hydrophobic. Hydrophilic means it loves water. So the polar side is going to love to be towards the water, and it can help dissolve in there, and the nonpolar side can help dissolve the grease off the surface. So what happens is we have this soap floating around, and it will put its nonpolar side towards the nonpolar grease. It put its hydrocarbon tail towards the grease, and eventually it kind of starts to lift that grease off the surface and surround it. So we have little soap spots surrounding our grease, kind of going around it, and then the part that is polar, that the water likes, is going to be facing on the outside. So you'll make little like droplets of stuff surrounding, of these little soap structures surrounding the grease droplets, and that lifts the grease off the clean surface. So where soap has both ends, a polar and a nonpolar end, you can use it to dissolve polar or nonpolar substances because it has both ends, so it can help dissolve both those things. This is also how stains work. So if you can look here really quick, you can pause it and look some more if you want. But so most of the time, if you just think about like how to remove a stain, just think about I need to use, if it's a polar substance that caused the stain, I might be able to use water if that's strong enough, depends on the color, if my color is not polar. But I might be able to use water because water is polar, so I can remove it. If it's a nonpolar substance that you spill, you might have to use nonpolar substances to remove it, like acetone. The next thing is chromatography. This is really fun. We just use chromatography. It's a method for separating components of a mixture. Different components of the mixture move at different rates and they separate from each other. So that allows us to see the different things. So a lot of times we use it to see colors. So because colors are the easiest, most obvious thing to see. So different colors move based on their polarity. They'll move at different rates across whatever our substance here is. And then when they move across that substance really fast, we can see the other colors. They'll separate out of theirs because they all move at different rates depending on their polarity.